Okay, I forgot to hit record, but our problem was, we've got a 1,000 kilogram satellite. And we want to find its potential kinetic energy, total energies in circular orbits, 10,000 kilometers, 8,000 kilometers, 6,400 kilometers. Well, these are orbits. This is sitting on the launch pad, moving at 500 meters per second due to the rotation of the Earth. Hopefully we launch in the direction of rotation to save energy. Sometimes we do it the other way, but almost 99% of the time, we're going to launch in the direction of the Earth, so we don't have to use as much fuel. So how do we do this? Well, some people just wrote down potential energy is negative big G, big M, little m over R. You should understand that that comes from integrating this expression with respect to R from 0 to infinity, or from R to infinity. Because that gives you the work done by gravity, and the potential energy is equal to the negative of the work done by gravity. And you should reason that out every time you think about it. It's a fundamental principle. It's going to come back again with fluids. It's going to come back again with electricity and magnetism. You want to incorporate that because it cuts through a lot of confusion. It replaces a dozen equations if you have that insight, and makes those dozen equations obvious and clear. Okay, so you should be able to integrate this to get this. Centripetal force equals the force of gravity in a circular orbit, because in a circular orbit, you have to have a centripetal force. You have to have a centripetal force to put a mass into a circle, to hold a mass in a circle. That centripetal force comes from the Earth. This applies only to circular orbit, does not apply to elliptical orbits, and most orbits are elliptical. Okay. But here, we're going to deal mostly with circular orbits, although you've seen a problem where you have to figure out, use the angular momentum to figure out, given the speed at perigee, find the speed at apogee, or vice versa. Talked about that last time, so review that if you need to. In any case, when you solve this equation, which everybody did correctly last time, you get this. 10,000 kilometer orbit, then find the potential energy. We plug in R equals 10 to the 7th meters because we know big G and big M. Of course, I'll give you big G and big M on the exam. Put a few little things up at the top, constants you need to know. And if I forget to put them up there, just use big G and big M. So in terms of big G and big M. Okay, so 10,000 orbit, you kilometer orbit, you can put it in, and you get a negative value for the potential energy. Then you go to the 8,000 meter orbit, you plug it in, and you can do that yourself. You get another potential energy. Now, potential energy you get here is negative. Potential energy here you get is even more negative, meaning that the potential energy increases as you go from here to here. You go from a lower negative to a higher negative. And the maximum possible potential energy is 0 at infinity. Got to get that picture in your head. You want to look at atomic orbitals and stuff like that. It's very confusing if you don't have that picture in your head. This is a good place to get it there. Okay. Now at R equals 6.4 times 10 to the 6 meters, you have even a lower potential energy. It's negative and lower. So you got to increase potential energy to get up to here. You got to increase potential energy again to get up to here. Just an overview, 3 orbits. You understand that? You know, it's a good start. All right, well, and you have formulas. You know, this V equals square root of big G, big M over R. Here, I emphasize, okay to memorize this formula, but if you forget it, you should know where it comes from, because you can write down these equations very easily and solve for V. Okay, you did it last time. You should be able to do that anytime you need it. It's a deeper insight, and it's more compact. one insight is worth a dozen formulas. Well, not always a dozen, sometimes more than a dozen, but understand the principle and where these things come from. You have to remember less. Okay. And balance that out as best you can. You get almost a month till the final. Okay. Kinetic energy, then you plug into this and you get this. Okay. Plug this into 1/2 mv squared and you get this. So that's where your expression for kinetic energy comes from. You're going to find that for the larger r, you get a lesser velocity. So to move from one circular orbit to another, you got to speed up in this orbit, but that takes you into higher orbit, which uses more potential energy than the kinetic energy you added. And that's something you need to kind of sort out. But first, you got to be able to do all this. And then, of course, at the 500, on the launch pad, you just find your kinetic energy, 1/2 mv squared. Now, how much energy does it take to get up there? Your rocket weighs hundreds of times as much as your silly little satellite sitting up there at the very tip. Okay? You got to use 3 stages. Your first stage burns for a couple of minutes, gets you up 10 kilometers or so. You got to go up at least 100 to get into low Earth orbit, preferably about 200 if you want to stay in orbit for a while. All right. And I'm learning things, reading this very good science fiction by this one author. Okay. The most recent is mind blowing. Okay. The chapter I read last night. I can't tell you on camera what it says, what it's about. But very entertaining. And a really, really neat insight. Okay. But one other aspect of one of his other books is they put these guys into low Earth orbit with the only rockets they have available, which are ICBMs, intercontinental ballistic missile. Okay, they can take a bomb from here to wherever we want to send it. Okay, if you put a light enough thing on the end of it, you can get it into low Earth orbit. The light thing they put on the end was basically the people they were sending into orbit in very special suits with a little bit of a shield. And the description of the whole process of getting blasted into space in one of these things is, really pretty interesting. It's very violent. And the thing gets me too is that the thing I read, and I forget just where it was, which was just recently in this series of 2 of the guy's novels. They're like 1,000-page novels. Okay. Is how inefficient rocket engines are. Okay, you just like, okay, you're blasting stuff out here. Impulse momentum gives you an impulse in this direction, conservation momentum. Pretty straightforward, ought to be pretty efficient. No, not very efficient at all. And he goes into some details about why. So the energy you need to get this thing into orbit is at least 1,000 times the energy difference you get from launch pad to one orbit or to another. The fuel you need to burn. Pretty amazing. Okay, that's just a side comment. I'll tell you a thing about differential equations, which is interesting, but I'm not going to. go into the details. Okay, the other problem, you simply have this, which is simply mx double prime equals negative kx. It's your basic simple harmonic motion, the basis of it. On the back of this last board, I have the derivation I did in class last time. Some people did a derivation, by finding a characteristic equation and so forth. Okay, I would have done it with symbols rather than with these numbers, and then plug the numbers in at the end because it's much easier. And then you can see clearly what the units ought to be. But not everybody is taking differential equations. So the calculus 1 exercise is simply, I give you a formula and saying that x equals something times the cosine of omega t. And tell you, take this and plug it into the equation. Okay? And it becomes very, very simple. If you remember the chain rule, if you haven't done calculus for a while, you might lose track of the chain rule. But in my opinion, that kind of leads to the conclusion that we need to assign more problems to give people more practice so they retain knowledge of what they're doing beyond the calculus course. Okay. And maybe some conceptual reasons why the chain rule is important, but it's hard to do that when you got students who can't see the forest for the trees because the trees got them completely surrounded. Okay, there are reasons for that, and it's not necessarily. Well, my point is, you got to learn to retain things. You got to learn to understand things at a deep enough level that they're there for you when you need them later. And it's a work in progress. Okay, so that aside, okay, so x equals 20 centimeters. Cosine of omega t. I'm not going to explain the chain rule. X prime equals 20 centimeters times negative omega sine of omega t. X double prime equals 20 centimeters times negative omega squared cosine of omega t. If you have to review the chain rule, do, because I'll not hesitate to give you problems involving the chain rule on the exam. Okay. Or problems involve simple integration. You know, not going into integration by parts and trig substitutions and all that stuff, but just basic simple integration using some fairly obvious substitutions. Okay. And probably not, fairly simple. But be prepared for that sort of thing. Okay. So now we have, I'll use some symbols here. I mean, the quantities, 2 kilograms times negative 20 centimeters times omega squared cosine of omega t equals negative of 100 newtons per centimeter per meter times 20 centimeters times cosine of omega t. Now, what's the obvious way to simplify this equation? I'll let you think about it for a minute. I'm not going to put anybody in the spot by asking anybody to answer, and I don't want to pause the video. Stop and think for a minute. Where's the obvious simplification? Okay, well, it should be obvious. You divide both sides by cosine omega t and both sides by 20 centimeters. So they're gone. And you have 2 kilograms. Times omega squared equals negative 100 newtons per meter. So omega, and this should be negative over here. Got a negative sign here, negative sign here. This negative sign came from doing 2 derivatives of a cosine. And this negative sign was already there in the original equation. So you get omega equals you get 100 newtons per meter over negative 2 kilograms. Well, negative 2 goes in 150 times. A newton is a kilogram meter per second squared, and a kilogram is a kilogram. So you get reciprocal second squared. No, it's a square root of this. That's going to give you approximately 7.1 reciprocal seconds. Which is 7.1 radians per second. Why is it radians? Well, one reason is omega is something you multiply by t to get an angle. Angles are in radians. We're doing calculus, we're doing mathematics. We're not doing degrees. Degrees are handy when you're doing some statics and stuff like that. But radians, when you're talking about any kind of motion. Well, any kind of circular motion. Okay. Well, there it is with all the units. Now, it would really be easier to solve this if you just used M for this and K for this and did the whole calculation with M and K. Then you would have seen that omega is the square root of K over M. And you really need to do that. It's a simple exercise. And you just start with the idea mx double prime is your net force. Negative kx is the net force. In this case, for simple harmonic motion. This is the only way you get simple harmonic motion. Simple harmonic translational motion. Simple harmonic rotational motion, you replace m by moment of inertia and k by a kappa, which is a Greek letter that looks a whole lot like k. And then x equals a cosine omega t. Like this in here, and you find that omega is the square root of k over m, which is not something you just memorize, something you understand from the principle that this is net force equal to restoring force, which is the condition for simple harmonic motion. So first thing you got to know about simple harmonic motion. Then just be able to verify this. And it also works if X is a linear combination of these. Since these are both solutions to the equation, and it's a second order equation, you have two arbitrary constants, which are this and this. And I stopped at the point of showing where the two arbitrary constants came from when I derived this thing in lab last time, using e to the IK2. Okay. This derivation is so simple that you should not go into anything regarding simple harmonic motion without knowing it. Because then everything else all in your lab. Okay, I'm going to show you how that works. So you're still writing, so I just got this little board here, that's all it should take. You know, this is really what you need to know. What we did here was just an example of it, and it works the same every time. So now that we know okay, I've written a couple more things. I'll just get those. All these different forms work. You can plug any of these into this equation and it works. Okay? With omega equals square root of k over m. B times the cosine of an angle plus C times the sine of an angle can be written as A times the cosine of omega t plus phi being the phase angle, or X equals A sine of omega t plus phi being your phase angle. And the phase angle, if you use the cosine, and the phase angle, if you use the sine, just differ by 90 degrees. And that's simple high school trigonometry. Not the simplest high school trigonometry, it's fairly solid high school trigonometry, but it's just sum of two angles formula and all that stuff. Okay. Yeah, I don't remember what those formulas are, but I can derive them from Euler's identity in seconds. Okay. Just an example of, I don't want to clutter my mind with those formulas. I knew them well when I graduated from high school. I knew them well when I was in college. I don't use them for a while. I let them go because they're easy to derive. It's something you should strive to be able to do. But I won't lose sleep over it right now. Okay. Again, it's just the principle, same as the principle of if you know this, then everything develops. You don't have to remember a bunch of formulas, and you understand the formulas when you see them. and then you know when to apply them. Okay. So here we got this. Well, x is implicitly a function, it's explicitly a function of t. So there's your velocity formula. This is your equation of motion. It's not 1/2 at squared plus bt plus c or whatever. Okay. It's not an equation you get from assuming that the acceleration is constant. Acceleration isn't constant. Acceleration is x double prime, which in this case it better not be constant, because if it is, this side is zero. Okay. Oh, yeah, I'm sorry. If acceleration is constant, x double prime being the acceleration would have to be constant, and kx is not constant, right? So again, don't pull out the equations of uniformly accelerated motion when you're dealing with simple harmonic motion or any other motion that's not characterized by constant acceleration. There are your equations of motion. And then energy. Relative to equilibrium, equilibrium is where x equals zero. Why is equilibrium where x equals zero? Because equilibrium is where acceleration is zero. Your acceleration is x double prime, and the only way the acceleration here is going to be zero is if x equals zero, right? So x equals zero at your equilibrium position. Well, relative to the equilibrium position, the potential energy is 1/2 kx squared. That's something you saw back in the chapter where we did a little bit with elasticity and so forth. It was the first potential energy formula that differed from MGH in your text. Okay. So we got right now 3 different potential energy formulas. We got 1/2 kx squared, that's for spring or pendulum. For pendulum, K is mg over L. We have negative big G, big M, little m over R for gravitation. And we have mgy or mgx or mgh near the Earth, near the surface of the Earth, or near the surface of a planet. You'd have to specify which G you're talking about. Now, total potential energy for your simple harmonic motion is 1/2 Ka squared. A is your maximum value of x here relative to equilibrium. That means if you're going out to here, then you're coming back to here. A is the same. A cosine of omega t goes from A to negative A back to A, negative A. Because the cosine goes from 1 to negative 1 and so forth, right? Do we understand that? Cosine can be at most 1 and the least is negative 1. And it goes 0 in between. We understand that. We understand the graph of a cosine. Okay, so there's your total potential energy. So your kinetic energy well, your potential energy at equilibrium is 0. Kinetic energy at x equals plus or minus a is 0 because the potential energy is equal to the total energy at that point. And another way, you swing out to here and you come to rest before you start swinging back. What's your kinetic energy when you're at rest? It's 0, right? Okay. So kinetic energy at x equals plus or minus a is 0. Find the kinetic energy at any x. It's 1/2 Ka squared minus 1/2 Kx squared, which is your potential energy at the extreme, or your total energy minus your potential energy at x. So let's just write that a little differently. Just unpack it a little bit. Total energy 1/2 Ka squared. I'll write U of x potential energy at position x is 1/2 Kx squared, which we already said.
Maybe it's this, maybe it's
At any point, U plus K is 1/2 Ka squared. At position x, your kinetic energy is 1/2 Ka squared minus 1/2 Kx squared. Now understand, you got to think a little bit about this and use it and apply it in problems before it really makes sense to you. But the structure of this analysis is very simple. Total energy is this, your kinetic energy or your potential energy at position x is this. So the difference between your total energy and your potential energy is your kinetic energy. Okay. I'm not even sure I said my words right a minute ago. Kinetic energy is the difference between total energy. A little more explicitly, kinetic energy at X is the difference between the total energy and the potential energy at position X. There's your total energy, there's your potential energy at X, and there is your kinetic energy. Okay? You want to digest that. You want to understand that as thoroughly as you can because it makes some of the problems really easy to answer. Okay? We go just a little further. Let's note if we replace, I'm going to factor out the 1/2 K. And I'm going to keep the A squared here because I'll have an A here, but this is just A squared minus X squared. I could write that here. Written a little sloppily. I think your chapter summary might well have that somewhere in the chapter summary. And of course, this is K. That's big K. This is little K.
Yeah, like some that are. Fine. Here. Hybridization.
We can factor out an A squared after squaring this. We'll have an A squared. We'll have a cosine squared omega t plus phi.
So, putting that out, let's say.
And that's 1/2 K A squared. Well, 1 minus cosine squared is a sine squared, right?
I really don't care. Just something that we do a little bit of scientific research on.
And
make it short.
A times the sine of omega t plus phi is a magnitude of your speed. Now I'm running out of room here to develop this. It's 1/2 K times V squared. And there's a little trick. Something's a little haywire here. This thing's interconvertible. It's not coming out. Should come out 1/2 mv squared. I've done some bonehead thing. I've left something out. But it's kind of neat. If you just analyze this and use the fact that 1 minus cosine squared is a sine squared, you end up with 1/2 mv squared, even though it's not what I ended up with. I have to think that through. I'm not going to puzzle over it right now. Okay. No, that's, you don't have to know that right now, but it's, you're going to see it if you read your book. You're going to see all this if you read your book. Look at the chapter summary and so forth. Okay, so we're just about out of time. That's a scheme of simple harmonic motion in a nutshell. And there's more you can do with it, but that's the framework. And if you understand the framework, you're going to have a better idea how to solve the problems. And there'll be problems too. I have a few simple ones due for Wednesday, and then a couple more complicated ones due for Monday, and that'll be your last text assignment. Okay, so again, you can expect a video for next time. Expect you to work through it as if you were in class. And then Monday we'll wrap things up. Of course, Friday we have our last lab, and we'll be incorporating a lot of this stuff into the lab. You have the analogy with the physical pendulum, which is what we observed back over there. Okay, we had the beam and put weights on it, measured the angular velocity. We also had a really interesting simple harmonic motion up here where we had the rubber bands on the floor with Drake stomping on the paper clips, okay? Or, you know, holding the paper clips constant. And it got into a phase where the rotation was extending the rubber bands, and then the rubber bands were pulling it back. Okay. Oh, one more thing. Too many things going on. I need to get this installed. Those files on the interface were not text files. They're proprietary files. And I have the program to unlock them, but my computer won't let me install them. So I've got to go find our network guy. All I have to do is put in administrative password and it'll install. And then I'll be able to get you some really interesting stuff. So hopefully I'll get that to you before Wednesday. But I've got videos and stuff to do, so we will see.